Okay, so our next speaker is Yiwei She, and she will talk about points.
Okay. Right. So this is to a general audience. So I've tried to make it as elementary as possible. The points on this elliptic curve forms a group. If you ask that the 3 points of intersection with a straight line add up to 0 in the elliptic curve. Okay. And the question is, how many points are there on this elliptic curve with coordinates in F3, I guess 3 to the d. And so we're going to compute this by using a theorem that is a formula for this number. And it tells us that all we need to do is compute a polynomial, and the roots will tell us how many points there are. So the theorem tells us that this polynomial has coefficients in the integers and that the roots are a certain size. So in particular, the roots are the sum of the roots are bounded, and their product is 3, plus or minus 3. So we know this is what we know about the polynomial. Okay. Right. So sorry. You may have heard about this theorem before, and its proof goes something like this polynomial comes as the characteristic polynomial of the Frobenius endomorphism acting on some vector space. So that's how we're going to compute this polynomial today. So remember that these points form a group. And in particular, so if I intersect a vertical line with these points, I get negative points on the elliptic curve. Okay, they add up to the point at infinity. And if that vertical line becomes tangent to this curve, I get points that are that 2 times the point is 0. Okay, and so here are the 3 points that are 2 torsion on this elliptic curve, and along with the point at infinity, you get the group z mod 2z squared. So this horizontal line tells you how to add these 3 points of 2 torsion. And the Frobenius is just raising these coordinates to the 3rd power. Here p is 3. And so the Frobenius acting on this vector space is the identity. And the characteristic polynomial of the identity is t squared plus 1 inside z mod 2 adjoint t. Okay, so at this point, we've learned a little bit about this polynomial. It's so we didn't figure out what the constant coefficient is. These are both 1 mod 2, but I guess we learned that a is even. So we should just keep going. The next thing you can do is look at the 4 torsion. I can't draw a picture of the 4 torsion anymore, but I can give you a basis for these elements, and this I is the a square root of -1 inside the field of 9 elements, and so here is the group that is the 4 torsion on my elliptic curve, and so you can see that the 2 torsion are already here, and you can check that any of these points are actually on the curve. And you find these by, again, intersecting the points. Actually, you want to intersect your 2 torsion and be tangent, the other 2 points to be tangent with your elliptic curve. So I can act Frobenius on my basis elements, and I get another point on my curve, and I look at my chart and I see that it's a linear combination of my basis, and that's that one, and I do that to the second basis element, and I get another linear combination of my basis elements. So this matrix on the right is what I'm going to take to the next slide. So we get that the Frobenius is equal to this matrix inside the endomorphisms of Z mod for Z squared. Okay, so the characteristic polynomial becomes, we can compute is t squared plus 3. And now we have a new congruence. And remember that we had, this is what we had before about P of t. So now we can tell plus and minus 3 apart. And we can also tell what A is. It's the only thing that's 0 mod 4. And so we have the polynomial that we're looking for. And so we can go back to the question at the beginning and answer it. So when D is 1, our formula predicts 4 points. And when D equals 2, our formula predicts 16 points. And actually, we already saw all of these points. They're the 2 and the 4 torsion, respectively. And I think that's all I have to say. I should say something about what I do, because obviously I didn't do this. I think about arithmetic geometry. I've thought about K3 surfaces. This year I hope to find new projects to work on, and I really like to work out examples, so I hope I get the chance to talk to some of you. Thank you.